And the first thing we're going to do is a review of variance, standard deviation, covariance, and correlation. We'll talk about the computation, we'll talk about the interpretation, and we'll talk about the units. And then we'll get into our portfolio risk and return calculations. Let's review variance, standard deviation, variance, standard deviation, and we're going to look at the variance of height, we're going to look at the standard deviation of height, we're going to look at the covariance of height and weight, and then we're going to look at the correlation of height and weight. So I'll start with variance, and the idea is that I have a number of observations of people's height, and for each person I'm going to have their height, and from this I can compute a simple average, and then I'm going to take each deviation from the average and I'm going to square that. I'm going to sum these and I'm going to divide by n minus 1. And let's just talk about what we've got here. If the first person's height is greater than the average, then this is a positive number. I square it, it stays positive. I take the next person's height, and if this person is shorter than the average, I square it. Even though that was a negative number, it now becomes a positive number. I sum up all of my positive numbers. I divide by n minus 1 observations because this is a sample and not the total population, and this gives me my variance. Now my units are going to be inches minus inches, which is still inches, squared, which is inches squared, summed up, which is still inches squared, divided by a scalar constant, n minus 1 is still inches squared, and so my units are inches squared, and that's not super useful, so I'm going to take the square root of my variance, and this is going to give me my standard deviation, and my standard deviation is in inches, so that's pretty useful. Okay, next I want to look at the covariance, and I want to look at the covariance of height and weight. And so now for each person I'm going to take their height minus the average height, and now I have another set of data. For each person I not only have their height, but I also have their weight. And now I can take the first person's height minus the average height and the first person's weight minus the average weight. Now if the first person is taller than average, I'm going to get a plus, a positive number, and if the second person is also heavier than average, I'm going to get a positive number. When I multiply a positive times a positive, I get a positive number. And when the second person, if the second person is shorter than average, I'm going to get a negative height. And if the second person is also lighter than average, I'm going to get a negative number. And if I have a negative times a negative, I also get a positive. I'm going to sum these up, and again I'm going to divide by n minus 1. And so if it's the case that if you are taller than average and also heavier than average, or you are shorter than average and also lighter than average, if that's always the case, then I'm going to get a big series of positive numbers, and I'm going to sum them up and I'm going to get a big positive covariance. But what if it's the case that if you're taller than average, you are also, let's get out of there, you are also lighter than average? Well, if that's the case, then I'm going to get a positive number times a negative number. I'm going to end up with a negative number. And if it's the case that you are shorter than average but also heavier than average, then I'm also going to get a negative number. And so if this is what the population or the sample looks like, when I sum these up, I'm going to sum them up and get a big negative number. Or if it's sometimes you're taller and heavier, sometimes you're lighter, shorter and lighter, sometimes you're taller and lighter and shorter and heavier, then I get a whole bunch of positives and a whole bunch of negatives. When I add these up, I'm going to end up with effectively 0. So if there is a strong relationship between these two things, I get positive. If there is an inverse relationship, I get negative. Or if there's no relationship, I'm going to get 0. Now the trouble with the covariance, and there's two problems with it. One is it's kind of hard to interpret. They're related problems. It's kind of hard to interpret because here my units are, well, this is inches minus inches is still inches, and this is pounds minus pounds is still pounds. When I multiply them, I get this sort of goofy unit, inches, pounds. And it's hard to interpret what that unit, how to deal with those units. In addition, the magnitude of this number is going to be a function of the units that I choose. So it's difficult to interpret the magnitude of a covariance. And so what I want to do next is define the correlation coefficient of height weight. And I'm going to define that as the covariance of height and weight. Oops. How do I get out of that? Height and weight. There's this little button on the pen I keep accidentally pressing. Divided by the standard deviation of the height and the standard deviation of the weight. And so here I have the covariance divided by the products of the standard deviation. So let's look at what I've got here. The units in the numerator, the covariance is inches times pounds, is inches pounds. And the units in the denominator is, well, inches and pounds, always inches pounds. And so now I no longer have any units. And so the correlation doesn't have any units. In addition, the correlation is going to be bounded, meaning that this is the total amount, the covariance is the total amount that height and weight vary together, and the denominator is the total amount that these things vary. It's not possible for them to vary together more than the total amount that they vary, meaning this can't be bigger in absolute value than the numerator can't be bigger in absolute value than the denominator. And so therefore the maximum value for the correlation coefficient is 1. It can't be any bigger than 1. In addition, it can't be any smaller than -1, because even if they vary exactly opposite each other, they can't vary opposite each other any more than the total amount they vary. And so the correlation coefficient is going to be bounded by -1 and +1. And so two really useful properties. One is it's bounded by -1 and +1. The second is it has no units. It's just a coefficient number. And we intuitively understand what correlation describes. And so this makes correlation a very useful measure relative to covariance.